is your presenter Asloob Mudassar, and I am presenting slide number 17A of the course on atomic and molecular physics. This is a new series of lectures on hyperfine structure, and today is the first lecture of this series. In the today's lecture, I shall be covering nuclear spin angular momentum and nuclear magnetic moment, because these two quantities are strongly related with the hyperfine structure. Nuclear spin hyperfine structure. Influence of atomic nucleus on atomic spectra. Before this lecture, we have been studying atomic spectra in much greater detail. And in the today's lecture, and in the lectures of this series, that is the lectures on hyperfine structure, we shall be investigating the influence of atomic nucleus on atomic spectra. You know that Z appears, that is the atomic number Z appears in all equations for spectral energy terms of the atoms. This is what we have seen in all the previous formulas, that the energy of the terms depend on the value of the atomic number Z. There are other influences of the nucleus on electronic spectra called hyperfine structure. The measurement of a hyperfine structure requires a spectrometer of a very high resolution. So since a spectral hyperfine structure is very small type of splitting, we need a very high resolution spectrometers in order to observe the hyperfine structure splitting. Interference spectrometers were used before with a resolving power of the order of 10 to the power 6. With laser spectroscopy methods, high resolving power can still be obtained. Factors other than Coulomb field due to nuclear charge Ze that influence the electronic spectra are listed below. So you see that one factor is the nuclear charge Ze that influence the atomic spectra. And there are some other factors other than the Coulomb field that also affect the nuclear spectrum, and this is what I have listed them as. Nucleus moves around a common center of gravity, and the Rydberg constant becomes dependent on the nuclear mass. So it means that the Rydberg constants being dependent on the nuclear mass will be different from isotopes to isotopes also. Isotopes of same atom have different masses and thus have different terms and thus different spectral lines. The isotope effect is difficult to measure for heavier atoms. So you see that in the lighter atoms there is a well-defined separation or well-defined difference between the Rydberg constants associated with the different atoms of lighter atoms. And we can easily observe the isotopic effect through their atomic spectra. But for the heavier atoms, that is for the isotopes of heavier atoms, it becomes even difficult to observe this effect, that is the effect of the Rydberg constant. That is, it becomes difficult to identify isotopes of the same element when we are dealing with heavier atoms. Different isotopes have different volumes, and this has some effect on electronic spectra known as the volume effect. So you see that if you are considering different isotopes, then of course those isotopes will have different volumes, and the electronic spectra will then be determined by the volume effect. Density of nuclear matter is constant, so the nuclear volume is simply proportional to the number of nucleons in the nucleus. Density of nuclear matter is constant, so the nuclear volume, you see that here I am stretching on the word nuclear volume, is simply proportional to the number of nucleons in the nucleus. Different isotopes have different nuclear sizes. Due to this, there are different interactions between the nucleus and the electrons. So you see that all these things that I have presented in this paragraph are very straightforward and very easily understandable. These two isotope effects, what were those two effects? One is the isotope effect over here, and the second one is the volume effect. And I am talking about these two effects over here. These two isotope effects permit determination of number of isotopes. That is, using these two effects, we can determine the number of isotopes of an element, masses of isotopes, we can determine their masses, the abundances of isotopes of an element, and we can determine their abundances in the nature. That with what concentration they do exist in nature. So these are called the abundances of the isotopes of that element. So the two effects, that is the isotope effect and the volume effect, will help us to determine the number of isotopes, the masses of the isotopes, and the abundances of the isotopes of that element. Hyperfine structure refers to structural changes in atomic spectra which results from the existence of spins and magnetic moment of the atomic nuclei. So you see that here I am talking about two quantities that I am talking about for the first time in the course on atomic physics, that there are the quantities which we call the spin angular momentum and the nuclear magnetic moment. So the nuclear spin and the nuclear magnetic moment, these two quantities related with the nuclei, are actually the core functions behind the hyperfine structure. It means that the atomic spectra are further divided into further fine splittings, which we call the hyperfine structure, and the reason is what, due to spin angular momentum of the nuclei and the magnetic moment of the nuclei. So here I am associating, I am discussing two quantities which are related with the nuclei, and those quantities are the spin angular momentum and the magnetic moment of the atomic nuclei. These two nuclei will interact with the electronic spectra, and then of course the spectra is further splitted, which we call as the hyperfine structure. And in these series of lectures, we shall be discussing hyperfine structure in much greater detail. That is, we shall be discussing these two quantities, that is the spin of the nuclei and the magnetic moments of the nuclei, and their interactions with the electronic quantities will be discussed in much greater detail in these series of lectures. So you see that the two quantities, that is the will interact and will result will produce the hyperfine structure. These were postulated by Pauli in 1924 to explain the spectroscopic observations. So you see that the spectra which the Pauli observed in 1924, there were some lines which were associated with the hyperfine structure, and those lines were first explained in 1924 by Pauli by discovering the nuclear spin and the nuclear magnetic moment. In 1934, Schuller postulated the existence of electric quadrupole moment in the nuclei. So you see that another quantity, you see that we have been discussing magnetic moment. Now here I am talking about the quadrupole moment in the nuclei. The interaction of these nuclear moments with the electrons lead to an additional splitting of the spectral lines called hyperfine structure. So electric quadrupole moments in the nuclei. So you see that, remember this. Electric quadrupole moments in the nuclei will interact with the electrons, and then This will lead to the additional splitting of the spectral lines, which we call the hyperfine structure splitting. Now let's discuss the spin angular momentum and the spin and the magnetic moment of nuclei. So here I am talking about two quantities associated with the nuclei, and those quantities are the spin angular momentum and the magnetic moment of the nuclei. You see that when we were talking about electronic structures or the contribution of the electrons in the atomic spectra, we were discussing orbital angular momentum and the spin angular momentum, and the associated quantities were the magnetic moment, orbital magnetic moment, and the spin magnetic moment as far as the atomic spectrum were concerned. But you know that when we are taking into account the contribution of the nuclei, we are not talking about the orbital angular momentum, because there is no quantity like orbital angular momentum associated with the nuclei. So only one quantity that is associated with the nuclei is the spin angular momentum. So there is no orbital angular momentum associated with nuclei. So most of the time when we are talking about the angular momentum, it means that we shall be talking about the spin angular momentum. And of course, the associated quantity with that is the magnetic moment of the nuclei. The nuclear spin angular momentum is represented by capital I, is defined as the magnitude of the capital I, which is a vector quantity. Its magnitude is equal to square root of I into I plus 1. Outside that square root, we have h bar. You see that this is the very popular definitions that we have been given for the orbital angular momentum and for the spin angular momentum of the electrons. But you see that when we are talking about the nucleus, this quantity is referred to as capital I, which we regard as the nuclear spin angular momentum as a vector quantity, and its magnitude, you know, that is related with the spin quantum number of the nucleus as given in the square root sign. So that capital I in the square root sign is actually the quantum number, and the quantity capital I mod on the left hand side of equation number 17.1 is actually the magnitude of the spin angular momentum. So spin quantum number is on the right hand side, and the spin angular momentum, the magnitude of the spin angular momentum, is actually on the left hand side, and the quantities, these two quantities are actually associated with the nuclei. So capital I without vectorial sign is actually the spin quantum number, which may take integral or half integral values, and I may range, and if I ranges in the interval from 0 to 15 half, the atomic nuclei is referred to as stable. So you see that if the value of I, that is the value of the spin quantum number, lies in the range from 0 to 15 half, then the atomic nuclei will be referred to as the stable nuclei. In the presence of external magnetic field B, so you see that here now we are talking about the external magnetic field B, which we shall apply to the atoms. And then of course this magnetic field will also influence some quantities on the nucleus on the nucleus side of the atom. So let's see what are those quantities. So you see that in the presence of the external magnetic field B, only the Z component of I, that is the spin angular momentum, is measurable. So what happens when you apply the magnetic field B onto an atom, of course onto the nucleus? The spin angular momentum of the nucleus, which is represented by the vector I, actually starts its precessional motion about the magnetic field B. And when I starts precessional motion about the magnetic field B, then there are three components of the vector I. Those three components are referred to as the IZ, IX, IY, and IZ. And out of these three components, the two components which we call as the X and Y components, or more precisely, IX and IY components, are averaged to zero. And only one component, which is the Z component, which is along the direction of the magnetic field B, will be measurable. So you see that the Z direction or the direction of the magnetic field are the same in this case. So the Z component of I, as given in equation number 17.2, the Z component of I is equal to Mi into H bar. You see that we have been given such a relationship for the orbital quantities and for the spin quantities related with the electrons. Now you see that I am giving you the same relationship but for the spin angular momentum of the nucleus. So equation number 17.2 gives you the Z component of the spin angular momentum, which is equal to Mi into H bar. And you know that Mi is actually the spin magnetic quantum number of the nucleus. So Mi will take values from I to I minus 1 to I minus 2 and so on up to minus I. That is Mi will be equal to 0, plus minus 1, plus minus 2 and so on up to plus minus I. That is the maximum value of Mi will be equal to plus I. So how many combinations of Mi will have? It will have 2I plus 1. That is the nuclear spin angular momentum or the spin magnetic moment. You know that Mi is actually referred to as the spin magnetic moment of the nuclei, spin quantum number you can say of the nucleus, or the more precisely the spin magnetic quantum number of the nucleus has 2I plus 1 possible orientations relative to Z axis. So this spin vector capital I, how many orientations it will have when it starts precessional motion about the magnetic field B? It will have this capital vector I, that is the spin quantum, that is the spin magnetic moment of the nucleus, will have 2I plus 1 possible orientations, and due to that one, the spin magnetic quantum number Mi will also have 2I plus 1 possible orientations about the Z direction or about the magnetic field B, because the Z direction or the B direction will be the same. Mi, that is the spin magnetic quantum number of the nucleon or the nucleus, is the nuclear spin magnetic quantum number. Nuclear spin magnetic moment mu I is associated with the nuclear spin angular momentum I through the relationship as given in equation number 17.3. That is mu I is equal to gamma times into capital I. So you see that this is the vector equation. And if gamma is positive, which is the case in the field of for the nucleons, the gamma is usually positive. If gamma is positive, then of course mu I, that is the nuclear magnetic moment, and this nuclear angular momentum have the same direction. That is, they have the same orientation, as obvious from this vector equation given in equation number 17.3. Where gamma is actually the nuclear gyromagnetic ratio. Similar to the Bohr magneton, we define the nuclear magneton mu n. So mu n is defined as mu n is equal to E into H bar over 2 MP, where MP is the mass of the proton. And this is called the nuclear magneton. So mu n vector is the nuclear magneton and MP is the mass of the proton. So you see that we can also write mu n magnitude is equal to E H bar over 2 MP. And here you know that MP, which is the mass of the proton, is equal to 1836 times the mass of the electron. So we have substituted MP by 1836 times ME, and then we can rearrange the terms so that we can write mu n is equal to mu b, which is the Bohr magneton, divided by 1836. So it means that the nuclear magneton is 1836 times smaller than the Bohr magneton. And we can simply write that mu n is less than mu b, or nuclear magneton is less than Bohr magneton by a factor of 1836. So nuclear magnetic moment is given by, so I am writing equation number 5 by following equation number 3. But I am putting the value of a gamma explicitly in this expression. Gamma can be determined through spectroscopic data. So mu I in the vectorial form is equal to gi into mu n over h bar, and this vector is multiplied by the vector I. So I have substituted in the previous equation, that is in equation number 3, I have used the value of the gyromagnetic ratio, nuclear gyromagnetic ratio, where Gi is actually the G factor for the nucleus, mu n is the nuclear magneton, h bar is the reduced Planck constant. So you see that I have rewritten equation number 3 in the as given in equation number 6 as mu I is equal to gamma times I, so that I can define gamma. So gamma is equal to Gi into mu n over h bar, which is the nuclear gyromagnetic ratio. So you see that the value of gamma or the expression of gamma can be determined through experimental arrangements. So gamma can be measured, and then its experimental is its mathematical equations can be written down as I have shown in equation number 7. So Gi is equal to gamma into h bar over mu n. So here I have used the previous equation, that is the equation number 7 has been solved for the value of Gi, where Gi is actually the G factor, the nuclear G factor, because quantity I is associated with the spin of the nucleus. So Gi will be referred to as the nuclear G factor. And the nuclear G factor Gi has been defined by gamma into h bar over mu n, as shown in equation number 8. Now you see that as described in one of the previous paragraph, that how many that this I, that is the spin angular momentum of the nucleus, has 2I plus 1 possible orientations in the presence of the external magnetic field. So you see that these vectors in the figure on the left hand side, I have shown actually 5 vectors over here. And these 5 vectors are actually different orientations of the spin angular momentum vector I. And these vectors, you know, that will precess about the magnetic field B naught. The precessional motion will be like this. And I have shown these 5 vectors, these 5 spin angular momenta vectors, and their projections on the vector B naught or along the z direction is given by 2h bar, 1h bar, 0, minus 1h bar, and minus 2h bar. And on the right hand side of this figure on the left, I have written down the spin magnetic quantum number Mi of the nucleus, which is plus 2, plus 1, 0, minus 1, minus 2. So you see that here actually I am taking into account the value of the spin angular momentum to be equal to 2, that is I is equal to 2. So when the spin quantum number I is equal to 2, then the spin magnetic quantum number Mi will be equal to 0, plus minus 1, plus minus 2. That is, there are 2I plus 1 quantities of values. So I have written these values, which are 5 in number. So I have shown 5 values of Mi in this equation, which you can see that I have written Mi and I have labeled them as plus 2, plus 1, 0, minus 1, minus 2. These are the Mi values, and the values of the mi, its projection on the z direction is plus 2, that is plus 2 h bar. And when mi is equal to plus 1, then it is plus 1 h bar. When mi is equal to 0, then it is 0 times h bar. When mi is equal to minus 1, then it is minus 1 h bar. When mi is equal to minus 2, then it is minus 2 h bar. And these mi values, are actually defined by equation number 17.2. So these are the mi values, and their projection on the z-axis is given by these values. So if you have mi5 values, then it will be plus plus 2 h bar, minus plus 1 h bar, 0 h bar, minus 1 h bar, and minus 2 h bar, because mi will have 5 values: 0, plus, minus 1, plus, minus 2. Because I have taken in this example the value of capital I, that is the spin quantum number, to be equal to 2, as you see that listed over here. So nuclear spin is I, and I have taken the quantum number I to be equal to 2, that is the spin quantum number is 2. And then of course the possible values of mi are is equal to 0, plus, minus 1, plus, minus 2. And these are the observable components of the nuclear spin I. And you know that their observable components are the components which are the projections of mi on the z-axis, that is plus 2 h bar, plus 1 h bar, 0, and minus 1 h bar, minus 2 h bar. These 5 quantities, that is the magnitude of mi on the z direction, these 5 quantities are actually measurable quantities. So you see that these 5 values of I, which I have shown in terms of the arrows, will carry out their precessional motions about the magnetic field B. So 5 possible precessional motions of I will be around the magnetic field B. So 5 mi values will be listed, and their projections will give you the measurable quantities. Now you see that in the middle figure, I have given observable components of the magnetic moment mu I. And you know that mu I is actually I. So here you can write that mu I is equal to I over h bar is equal to mi. So you can define mi over here from one of the previous equations, because I, which is the z component, can be defined as mi into h bar, and this I is actually here the z component. So more precisely, you can write that the z component of I divided by h bar is equal to mi. So you see that I am writing down their values, the values of the spin magnetic moment mu I. So the values of mu I will be equal to 2 into gi into mu n, then the gi into mu n, that is plus gi into mu n, then 0, then minus gi into mu n, and then minus 2 into gi into mu n. And you know that these 2 plus 1, 0, minus 1, minus 2 are actually the values of the spin magnetic quantum number mi. And you know that if you plug in these values and the values of mu I in equation number 5, so you have a mu I, and on the right hand side you have gi into mu n over h bar into I. And you know that this I is actually I over h bar. So I over h bar can be written as mi. For example, here in this figure you can see that I can write I over h bar into mi. So in that equation you can replace I over h bar by mi. So then mi has 5 possible values, which are 0, plus, minus 1, plus, minus 2. And similarly you have mu I actually 5 values according to the values of mi, because I over h bar can be written as mi. So mi has 5 values, so mu I then will have 5 values, and these will be given as the projection of these five values onto the z direction. So we have these values as 2 gi into mu n, then plus gi into mu n, then 0, then minus gi into mu n, then minus 2 into gi into mu n. So then if you want to observe the values of the magnetic moment, spin magnetic moment, or the nuclear magnetic moment mu I, then of course you can measure these five quantities which have their projections on the z direction or on the v axis. And you see that on the figure on the left hand side, I have shown delta E, that is the separation between two consecutive levels. So I have shown actually four values of delta E, which is the energy separation between these five levels. Then of course you know that Vi, which is the potential energy of the magnetic moment in the field V naught. So you see that the potential energy is defined as V is equal to minus mu I dot with V naught. That is the potential energy is V is defined as V is equal to minus times the dot product of the spin magnetic moment mu I and the external magnetic moment B naught. Since there is a negative sign in the definition of the potential energy V, due to that negative sign I have inverted the directions of the potential energy V. So you can see that the negative quantities are on the top and the positive quantities is on the bottom side. And then delta E is actually the separation in energy between two consecutive levels. And actually these separation is actually a hyperfine structure splitting between two consecutive levels. So you see that here what I have defined delta E as the hyperfine separation or splitting for the first time over here in this lecture. Under the external magnetic field B naught along the z direction, only the z component of the angular momentum I, that is Iz, is quantized, which implies that only z component of mu I is quantized and is observable. So you see that when you apply B naught as an external magnetic field, then only the z component of the spin angular momentum capital I vector will be quantized. That is, its value can be measured and its values will be fixed along the z direction, depending upon the different orientations of the vector I. So the z component of those quantities are quantized. Since I is quantized, then of course the magnetic moment mu I will also be quantized, and these quantities, that is their z components, z component of I, which is Iz, and the z component of mu I, which will be mu Iz, those z components of I and mu I will only be measurable quantities. Their x and y components will be averaged out to zero during the precessional motion of these quantities. So you see that when I, that is the spin angular momentum, carries a precessional motion about the magnetic field B naught. Similarly, its counterpart, which is mu I, that is the spin magnetic moment of the nucleus, will also carry out a precessional motion about the magnetic field B naught. And I and mu I, you know, that will have the same direction. But you know that for the electronic quantities, for the electronic quantities, the total angular momentum J and the total magnetic moment mu J will have opposite directions due to the electronic charge, which is a minus. Now let's start with the equation mu I is equal to gamma times I. This is what we have discussed earlier. Now I am considering the z component of this equation. So mu Iz is equal to gamma into Iz. So you see that in the first step I have taken the z component of these two quantities. And you know that gamma times the z component of Iz will be equal to mi h bar, or you can write it as h bar into mi. So Iz I have taken from the previous one of the previous equation, that Iz was defined as Mi into H bar, or here I have written by changing their orders that Iz is equal to H bar into Mi. So I have gamma, and the Z component of Iz can be written as gamma into H bar into Mi. And the value of gamma, which is the spin gyromagnetic ratio of the nucleus, has been written over here. So Gi into mu n over H bar, then I have written H bar into Mi. And I have written H bar, which H bar, these two H bar will cancel out from the numerator and the denominator, and I shall be left with Gi into mu n into Mi. So this will give you, you know that I have found here the Z component of the spin magnetic moment of the nucleus as given in equation number 17.9. And on the left hand side, you can see that it is the Z component of mu I. And on the right hand side, you can see that it is equal to Gi into mu n into Mi. So the Z component of mu I is mainly determined by the magnetic moment, by the magnetic quantum number, by the spin magnetic quantum number of the nucleus. And if you want to take the maximum value of those components, then you can write the maximum value as I have written on the left hand side, that is mu I Z component, and I am taking the maximum value of that component is equal to Gi into mu n, and here I am taking the Z maximum component of Mi. And you know that the maximum value of Mi will be equal to capital I, because you know that Mi will change from 0 plus minus 1 plus minus 2 and so on up to plus minus capital I. So its maximum value will be plus capital I, which is which is what I have written in equation number 11. So the maximum component of the maximum value of the Z component of the nuclear magnetic moment of the nucleus, or the nuclear magnetic moment, will be equal to Gi into mu n into capital I. And here this capital I is actually the maximum value of the spin quantum number. So mu I Z and Z max is experimentally measurable quantity and has been tabulated. So you see that there are tables are available, and you can find out their values for different elements and for different nuclei more precisely. So you see that here I have the value, I have written the value of Z, I have written the value of delta E. And you know that delta E is what I have defined in this equation, that is the separation between two consecutive levels in a hyperfine structure is delta E. So you can, if you want to find delta E, you can subtract any two values on the written over here, and you can find out the value of delta E. And here you see that I have written the value of delta E as Gi into mu n into B into Mi into B naught. So you see that when you want to write the value of delta E, you need to multiply it with the magnitude of the external magnetic field B naught. And Gi into mu n into Mi is actually the Z component. From equation number 9, you can see that this is the Z component. Gi into mu n into Mi is actually the Z component of the magnetic moment, nuclear magnetic moment Mi. And if you multiply the Z component of the magnetic moment mu I with the external magnitude of the external magnetic field B naught, you can get the value of delta E. But you know that I have defined delta E over here, then you need to write delta Mi instead of Mi. So you can make a correction over here. That is on the right hand side, you can put the quantities delta Mi. So delta E is equal to Gi into mu n into delta Mi into B naught. And you see that I have also multiplied B naught in these quantities, where these quantities, that is the magnitude of, that is the Z component of mu I is 2 Gi into mu n, and here on the left hand side I have multiplied it with B naught, so that I can convert that one into energy terms. So delta E is actually the consecutive difference between two quantities, and then when you are taking delta E as the consecutive measurement, then of course delta Mi will be equal to 1. So you can write delta E, that is the separation between two terms in the hyperfine structure, will be equal to Gi into mu n into delta Mi into B naught. So if you are considering different Mi levels, that will be delta Mi. But if you are considering the two consecutive levels, then the value of delta Mi will be equal to 1. So delta E is actually hyperfine splitting energy. So you see that here, the first time I am going to define the formula for the hyperfine splitting energy delta E. So delta E is the hyperfine splitting energy and is measured from the hyperfine spectra. So knowing the value of B naught magnitude, that is the magnitude of external magnetic field B naught, knowing this value and knowing the value of Mi, you can find out the value of Gi into mu n as given in equation number 13. So you can solve equation number 12 for Gi into mu n, which is given in equation number 13 as Gi into mu n is equal to delta E divided by delta Mi into B naught. So again in the denominator, you need to make a correction that Mi will be written as delta Mi. Or you can omit delta Mi when delta E is defined for two consecutive levels. So between two consecutive levels, delta E of delta E, then you need to put delta Mi is equal to 1. But if you are considering different levels on the hyperfine structure splitting, then of course you need to put the value of delta, appropriate value of delta Mi. So you see that in equation number 13, it is obvious you can determine the value of Gi and mu n from the hyperfine structure splitting energy. So if you have the hyperfine splitting spectra, you can easily determine from those spectra the value of delta E and delta Mi, and if the external magnetic field B naught is known, you can determine the value of Gi and mu n. But you know that the value of mu n is empirically known to us, so you can find out the value of the G factor for the nucleons. So Gi, that is the nuclear G factor, can be determined experimentally. To determine this quantities, that is the maximum value of the Z component of the nuclear magnetic moment, using equation number 11. So let me show you equation number 11 over here. This is equation number 11. So you see that to determine the maximum value of the Z component of the nuclear magnetic moment, it requires the value of the nuclear spin quantum number I. So from equation number 11, you can see if the value of spin quantum number I is known, you can determine the value of the maximum value of the Z component of mu I. For hydrogen atom, the value of I is equal to half. That is the value of the spin quantum number is half, and the corresponding Gi value is 5.58. And from this one, you can write down the nuclear magnetic moment for the hydrogen atom is equal to 2.79 mu n. So for the potassium nucleus with mass number 40 has a value of I is equal to 40, and the Gi value is minus 0.32, and this gives you the value of magnetic moment of the nucleon of the nucleus for the potassium nucleus. The value of mu I is equal to minus 1.29 mu n. If Gi, which is the G factor for the nucleus, is greater than 0, then of course mu I is also greater than 0. And in this case, the spin angular momentum I and the spin magnetic moment mu I will be parallel to each other. So you see that under this condition, the spin angular momentum I and the spin magnetic moment mu I of the nucleus will be parallel to each other under the condition that mu Gi is greater than 0. That is, Gi is a positive quantity. If then, you know that I have written this quantities shown in equation number 16 for the case of the electronic spectrum. And on the left hand side, this mu can be written as mu J. If you are writing it mu J, you need to put the value of J on the right hand side. But if you are writing it for the orbital quantity, that is mu L. If you are writing the subscript with mu as capital L or small l, then mu L will be equal to minus E over 2m naught into L, where L is the spin, where L is the orbital angular momentum of the electron, and mu L will then be equal to the orbital magnetic moment of the electron. And if you are writing this quantities for the total angular momentum J of the atom, then this equation, that is the 16 equation number 16, will take the form mu J is equal to minus E over 2m naught into J angular momentum. So similarly, you can write this quantity for the spin. For the spin quantities, you can also write mu s is equal to minus E over 2m naught into S vector. That is the spin angular momentum. So since you know that for the electronic spectrum, we deal with the spin quantities, we deal with the orbital quantities, we deal with the total quantities due to spin and orbital quantities. So three expressions are what can be written for the quantities from equation number 16 for the three quantities. That is for the spin, for the orbital quantities as it is written in equation number 16, and for the total angular momentum J of the atom. And this is what we have discussed in much greater detail in some of the previous lectures. Now, for a nucleus with the Gi is equal to 1, you can write for the nuclear, the magnetic moment of the nucleus can be written as mu I is equal to plus E over 2 mp into I, where I is, you know, that is the spin angular momentum of the nucleus, and mp is the mass of the proton. To find the value of I, that is the value of the spin quantum number I, or more precisely, the nuclear spin, the quantum number associated with the nuclear spin or the nuclear angular momentum, is the subject matter of nuclear physics. That is, to determine the value of I is the subject matter of nuclear physics. Many nuclei have vanishing spin. That is, for many nuclei, value of capital I is equal to 0. That is the value of the spin quantum number or the spin angular momentum for many nuclei are equal to 0. Such nuclei do not contribute to hyperfine structure. That is, we cannot observe the hyperfine structure for some nuclei for which the value of total spin angular momentum of the nuclei is 0. And those atoms are listed over here. For example, helium, carbon, oxygen, calcium, iron, strontium, cadmium, hafnium, lead, and uranium. These are the elements for which the total value of capital I is equal to 0. That is, you cannot observe the hyperfine structure for these elements. So you see that I shall end this first lecture of the series of hyperfine structure at this point. So this lecture is continued, and I think that there will be 2 to 3 lectures more on the topic on hyperfine structure. So the lecture is continued, and this is the end of slide number 17A of the course on atomic and molecular physics, and the lecture is continued.